Hello everyone. Good evening. I hope I am audible. Can you hear me? Okay. Okay. Can one of you confirm? Lakshmi, Kiran, last Jedi Knight. Am I audible and uh, is my screen showing? Okay. Lakshmi says yes. Okay. Okay. Thank you, Lakshmi. So yeah. Okay. Again, hi everyone. Uh, and happy Independence Day, by the way. So, welcome to the live session for week 3. Okay, and today's topic is logic. Okay, so let us begin right away. So, what we'll do is we'll solve a few problems, about 10 problems in total. But like as before, I'll just do some quick introduction to the concepts. It will not be in depth. We'll just visit some of the few concepts that are there in the lectures already. Okay, so yeah, today's topic is logic. So, what is logic? So, logic is an important part of discrete maths. You will be seeing that it is used everywhere, left and right. Uh, Logic, or more formally, mathematical logic, talks about inferring different results based on previous knowledge. Okay, that is one way to put it. And there is a very formal way to do it also. Okay, there's a very formal way to do it also, but we as humans are naturally capable of deducing logical statements. So firstly we talk about statements, or more formally what is known as proposition. So what is a proposition? A proposition is a statement which is either true or false, but a proposition cannot be both at the same time. So a proposition cannot per se contradict itself. Okay, something like a famous example you might be hearing is something like the sun rises in the east. Okay, this is a proposition. Okay, because it's true. Okay, and whereas sun rises in the west, that is clearly false, but it's still a proposition. But if you hear something like a sentence like "go there," okay, it's not exactly a statement which is true or false, right? So go there. Okay, can you say it's like a? Can you say the sentence is true or false? Well, not exactly. So this would not count as a proposition. So here I've written an example. It is raining today. Well, given the context, it could be raining today or it may not. For example, right now in Chennai, it is not raining currently. So it is clearly false, but it is not both true and false right now. So this is clearly a proposition. Now, quickly, I'll just recap on some things. Now, we have two things here, a tautology and a contradiction. What is a tautology? Tautology is a statement which is always true. Okay. Yeah. So a good example would be the same, thing. The sun rises in the east. This statement is possibly always true. Given the lifetime of the sun and the solar system. So yeah. So this statement is what is called a tautology. And as you might have seen, if you make the truth table for a tautology, okay, if your statement depends on other propositions like a and b, okay, a and b could be 0 0 0 1 1 0 1 1, whereas 0 represents false and 1 represents true, then if the output f is a tautology, then it will always output true. F will always output true no matter what the combination of a and b. Okay. But similarly, what is a contradiction? A contradiction is a statement which is always false. So similarly, if we think about the truth table, and let's say f is supposed to be a contradiction, okay, then no matter what the no, one moment. Yeah. So no matter what the values of A and B represent, they may be true or they may be false. Okay. If F is a contradiction, the outputs of F will always be false. Okay. So yeah. So remember that the truth table. Okay. In case of a tautology, truth table has all ones. Okay. And in case of a contradiction, the truth table has all zeros. Okay. Now, as we've seen, the propositions can be, you can label a proposition to be true or false, but we can even do combinations of propositions. We use some special operators, logical operators for that, which are called connectives. Okay. So, firstly, we have the not operator. So, what does the not operator look like? Okay. Also called the negation operator. For example, if I have a statement like let's call this proposition P, and the proposition P is it is raining outside. That is my proposition. Okay. So if I apply the not operator, the not connective, logically what will happen? The negation of the statement, also called the complement of the statement. It is not raining outside. Okay. As soon as I put the complement here. And which means that if P is true, then not P is false. Similarly, if P was to be false, then if I add a not operator to P, it becomes true. Okay. So let us fill in the values here. 0 means false and 1 means true. Okay. So 0 means false and 1 means true. Let's say P was 0 first. Okay. So P is a statement which is false. Then not P will be not P will clearly be the opposite of that, which is true. So if P is true, then not P is false. If P is false, then not P is true. Okay, this is what we are using. And if P were to be true, which is represented by 1, then we just simply flip it, right? The not of that statement is simply false. Okay, so this is the truth table for not. Similarly, let's try it for other cases. Okay, so so how could the combinations be? P and Q may be both false. So P can be false and Q can be true. This is how we can fill it. P can be true and Q can be false, or both can be true. So these are the combinations here for two variables. Okay, and we are looking at an operator called AND, connective called AND. So what does AND do? AND gives true. Okay, AND gives true if all inputs are true. That means what do I mean when it is raining outside and it is cloudy, something like that. This statement is true if it is raining outside is also true and it is cloudy is also true. So what I do is if both my P and Q are false, okay, then clearly it is false. Then clearly AND is false because I want both P and Q to be true, remember. So if one is false and the other is true, then both of them are not true. Both P and Q are not true, right? So P and Q is false. 1 0 means true and false. Then this too is a false case because both of them are not true. And here both of them are true. If both of them are true, then what do we have? We have that P and Q is true. Now for the OR case, okay, 0 0 0 1 1 0 1 1. Okay, OR is true when either P is true or Q is true or both are true. Okay, that is how it is defined as. So you can think of it logically also. So here none of them are true. So clearly our answer is false. If either of them are true, so since Q is true here, then this P or Q is clearly true. Here one is true, so at least one of them is true. So I give the OR as true, and both of them are true. Then I give I fill it as true. Okay, I'm just doing a quick recap. Okay, so we'll soon move on to the problems. But if you want a more in-depth exploration, then please look at the lectures. Okay, or you can stop me and then ask if there is a doubt. Okay, so finally we have something called conditional. Conditional is P implies Q. Okay, this symbol is called implies. Okay, so what does this mean? If P is true, then Q is true. Okay, this statement is true if P is true and Q is okay. So 0 0 0 1 1 0 1. Okay, so here P is already false. So actually, since P is already false, it doesn't matter what Q is. So this statement is vacuously true. If P is false, then again we don't care what here it is. So this is vacuously true. But we are now saying that, oh, okay, P is true and Q is false. Okay, P is true and Q is false. But we are saying if P is true, then Q should be true also. Right? If P is true, then Q should be true. And we are saying P is true and Q is false. How can that happen? So it must be that P implies Q is false. Okay, and again P is true, Q is true, P is true, then Q is true, then this statement is clearly true. So yeah, this is the truth table for conditional. Okay, you can remember that the 0 is in the case that when P is 1 and Q is 0. Okay, otherwise it is always 1. Now we'll look at biconditional. Okay, or also called by implication. P if and only if. This is also called if and only if. Okay, P is true if only if Q is true. What does this mean? This means, in other words, P implies Q. Okay, that is if P then Q. Okay, or I'll write it as if P then Q, and if Q then P. Okay, so if these two cases, if if P implies Q, okay, or we'll see it from the truth table, 0 0 0 1 1 0 1 1. Okay, so here again 0 0. So P is already 0, so we don't care what Q is. Okay, so this is vacuously true. But here we get the case that 1 implies Q implies P. We have Q implies P here, right? If it is so that Q implies P, then then P should be true, but here P is getting false. So here we have a 0, and here again, like the previous implication case, we have that if P is true, then Q is true. But here we are saying P is true and Q is false. How can that happen? So this statement is false, and again here this statement is vacuously true. So this is the truth table for biconditional. XOR case. Okay, so 0 0 0 1 1 0 1 1. Okay, now let us see this. XOR means P is true or Q is true, but not both. So P is true or Q is true, but not both. So here P is false, Q is also false. So none of these settings are getting captured, right? Both of them are false. If both of them are false, then clearly XOR is false. Or in other words, XOR will give 1 if either of the inputs are 1 but not both. So here we have that either of the inputs are 1. right? One of the inputs are 1 but not both, so this is true. Okay, here too we see that P is true, Q is false. So here X, so either of the inputs are 1 but not both, that is still satisfied. Okay, here we have both of the inputs are 1, so this is where it differs from OR. Okay, and here we have a 0. So this is the truth table for XOR. Okay, now you must have seen it in the lecture. I'm just quickly writing these things. Okay, if P then Q can be logically written as, or logically it is equivalent to, not P or Q. Okay, so if I have such a operator, P implies Q, then I can always write it as, okay, this, not P or Q. So this is a useful technique that is used in logic. Okay, another thing, like I said earlier, what does by implication mean? P by implication Q means, in both direction, P implies Q and Q implies P. So this is nothing but P implies Q and Q implies P, but we can always write P implies Q as this, no, not P or Q. So let me simply write it as not P or Q. Okay, and next thing, what do we have? Next thing we have Q implies P. Okay, we have AND, so I'll write an AND. So next thing, what do you have? You have Q implies P. Q implies P can be written as not Q or P because of this result, right? So I'll simply write not Q or P. So this is another way to write by implication in terms of on and or and not. Okay. Next, we have P XOR Q. What is P XOR Q? P XOR Q says that either A is true or B is true. So P is not true and Q is not. Q is true. Then give a 1. Give a true. Or when P is true and Q is false, then give a 1. So this exactly captures XOR. It will never happen, if you observe, it will never happen that P is true and Q is also true, because this is against what XOR says, right? XOR says that both cannot be true. Okay, so finally what we have is, if you have P implies Q, I can flip them. I can bring Q to this side, I can bring P to this side, provided that I negate both of them. This is what is called contraposition, which is very important in discrete mathematics. Okay, so P implies Q is logically equivalent to negation of the RHS. Okay, not Q implies not P, the negation of the LHS. Okay, so this is an important property we'll see in all the places in logic, and it is an important tool that is used to prove a lot of theorems also. But let us continue. Okay, so let us now try to solve some problems. The problem is as follows. P, the proposition P says, okay, the message is scanned for viruses. What does Q say? Q say the message was sent from an unknown system. Express the following statement using logical connector. Let me write that again. What is P? The message is scanned for viruses. Okay. And what is Q? Okay, one moment. Yeah. And what is Q? And yeah. Okay, what is Q? Q is the message was sent from an unknown system. Okay, so now what we need to do in terms of P and Q, we need to represent these statements. Okay, so yeah, let's try the first one. The message is scanned for viruses whenever the message was sent from an unknown system. So I'll try the first one. Yeah. The message is scanned for viruses. So which proposition does it correspond to? P, right? The message is scanned for viruses is P. So the statement in A is P. Okay. Whenever the message was sent from an unknown system. So what proposition does it correspond to? Whenever it was sent from an unknown system, the message was sent from an unknown system is simply Q. So the statement says P whenever Q. But what is whenever? Okay, I can write it as, this is simply logically equivalent to P if Q, right? Okay, P whenever Q is simply P if Q happens, which is equivalent to if Q then P. Okay, but what do we know about if Q then P? If we look back, it is nothing but conditional, simple implication, right? So what do we do? Q implies P is the answer. Okay, similarly, let's look at the second one. Okay, the second one says the message was sent from an unknown system, but it was not scanned for viruses. Okay, this too is a simple one. Can you guys try it once, and I'll give you a few seconds. Maybe you can try B, part B, one part B. The message was sent from an unknown system, but it was not scanned for viruses. How do you represent this in terms of P and Q? So what is P? P is that the message is scanned for viruses, and Q is the message was sent from an unknown system. Okay. So anyone? Negation P. Lakshmi says negation P. Okay. So negation P. Let's try that. What is P saying? The message is scanned for viruses. Okay. So what is not P? So P is the message is scanned for viruses. Not P. Okay. Will represent the message is not scanned for viruses. Right. What does the statement say? But it was not scanned for viruses. So yeah, you are right, Lakshmi. This part is negation P. Good. But we are still left with this part. The message was sent from an unknown system. Now I'm not P part is done. So how do I do this? The message was sent from an unknown system. The message was sent from an unknown system simply corresponds to Q, right? Q means the message was sent from an unknown system. So what I'll say is this: Q and, okay, and not P. Okay, why? Because Q means the message was sent from an unknown system. Okay, the message from was sent from an unknown system, and okay, and is as good as but logically, right? And it was not scanned for viruses, is simply not P. So what is my answer? Or mathematically Q and not P. Okay, yeah, good. So yeah, let us look at C. It is necessary to scan the message for viruses whenever it was sent from an unknown system. Okay, it is necessary. Okay, to what? To scan the messages for the viruses. What does this statement uh, show in terms of P and Q? Scan the message of viruses is simply the statement P, right? So it is necessary to do P. Okay, necessary to do P whenever, okay, whenever it was sent from an unknown system. It was sent from an unknown system is simply Q, right? So Q is simply it is sent from an unknown system. So it is necessary to do P whenever Q happens. So this is similar to the part A1, right? So P necessarily happens if Q happens, meaning it is nothing but Q implies P. That is, if P is true, then Q is true. Sorry, if Q is true, then P is true. I hope this is clear. Okay. Um. Okay. I'll let you guys try this one. Okay. Um. So the question is, when a message is not sent from an unknown system, it is not scanned for viruses. Can you try this one? When a message is not sent from an unknown system, it is not scanned for viruses. I'll give you a few seconds. So look at P and look at Q and then look at the sentence. So always if such a okay, Lakshmi say negation P implies negation Q. Okay. When such a sentence arises, break them up. Try to locate where P and Q are. Madhav negation Q implies negation P. Okay. So Lakshmi says negation P implies negation Q. Madhav says Q negation Q implies negation. Let's see. Okay, I'll give like 5 more seconds. Try to locate where P and Q are. Okay. So yeah. When a message is not sent from an unknown system, it is not scanned for viruses. When not sent from unknown system, it is not scanned for viruses. Now, not sent from unknown system, which is the predicate that corresponds to sent from unknown system. Sent from unknown system is simply Q, right? So this statement is simply Q. But remember that there is a not here. Okay. So firstly, what do I have? It is some not Q is there, sitting somewhere. Next. Then, when not sent from an unknown system, then it is not scanned for viruses. What is scanned for viruses? If a message is scanned for viruses, it is simply P, right? So this part is P. But again, remember, it has a not here. So what is my answer? When can be interpreted as if. Okay, when it is not sent is as good as if it is not sent, then something. So not Q, then, okay, if not Q, then it is not scanned for viruses, which means not of P. So this is the answer. Not Q implies not P. Yeah, I think Madhav was correct. Yeah, and not Q implies not P. And any idea what I can also write it as? If I have not both sides of the implication. So I'll go P implies Q. Right. Good. Yeah. Yeah. Good luck. So remember when I talked about contrapositive a while ago? This is exactly where we can use contrapositive. See, not P implies not Q is logically equivalent to P implies Q. That means I can flip, the implication and negate both sides, and the logic is same. So what can I write it as? P implies Q. Flip Q and P and negate both of them. Okay. And so this is quite interesting also. You can think of it in terms of sentences also. So this sentence, okay, sorry. So this sentence, okay, is actually logically equivalent to saying P implies Q. And what does that mean? If it is scanned for viruses, then it is sent from an unknown system. So yeah, we can bring in these interesting kind of mathematical conclusions. So yeah, I hope everything was clear from that section. Let's do another one regarding propositions. Okay, let P and Q be propositions such that P is you have the flu, Q is you missed the final examination, R is you passed the course. Using logical connectives, how does one write if you have the flu, you will miss the final examination and fail the course? Okay, so this is what we need to write. If you have the flu, you will fail the examination and fail. You will fail the examination and fail the course. Okay, using P, Q, and R. So yeah, if anyone has an idea. Option C. Option C. Okay. In the right direction, but look more carefully. Kiran Kumar also says option C. Okay. Kiran Kumar also says option C. Okay. Let me give like 5 more seconds. Okay. So yeah, I mean, both of you are almost correct. Good. So if you have the flu, okay. So it's saying if you have the flu. P is if you have the flu. Okay. And let me write answer here. So definitely if you have the flu is there. So P is there. Oh, sorry, if won't be there. Since if then is there, okay. P, then if P is true, then something happens, okay. Then you will miss the final examination. Okay. So what is miss the final examination? If you miss the final examination is Q. Q is simply miss final exam, then Q, okay, and fail the course, and fail the course. What is R? You will pass the course. If R is you will pass the course, how do I represent that you fail the course? Failing is the opposite of passing, right? Failing is the complement of passing. So what does this mean? This means that negation R, okay, or let me write it better. Negation R is you fail the course. So that is exactly what my statement is saying. You fail the course. So, and not R. But now, be careful when you translate it into logical connectives. Because option C says the following. P implies Q. Yeah, good luck. And not R. And what is this? This is option C. Okay. Option D says P implies. So clearly option 1 and 2 are not true. Okay. They are talking about something totally different. So clearly option C and D may be true. Okay. So D says P implies Q and not R, but these are in brackets. So what is the difference between them? Okay. The difference is as follows. The first one says if P, then both Q is true and not R is true. Isn't that what we are trying to say? If you have the flu, then it is true that you will miss the exam also. And since you had the flu and you missed the exam, you'll fail the course also. Isn't that what we are trying to say? Whereas, what does option C say? If P is true, then Q is true. Okay, this is separate. And it is true that you will always fail. You will always fail the course. So this is separately said and this is separately said. So it's like I'm saying that, if you have the flu, you'll miss the exam. But no matter what you do, you will fail the course. Because this shows that this is a separate entity. This is a separate statement. Okay. So you will always fail the course, but if you have the flu, then you will miss the final exam. That is what is meant. So remember, look at the bracketing. So that is why bracketing is very important. Okay. So if you have the flu, then it is true that both these cases happen. So yeah, good. So answer is option D. Why? This is independent of P. That is the reason. Okay. Okay, I hope that was clear. Any messages? It is option D. Yeah, Lakshmi. Okay. So not P by implication Q is equivalent to not Q by implication P. Okay. Not P by implication Q is equivalent to not Q by implication P. P implication by implication not Q. P implies Q. Q implies P. Okay, let's see what this is equivalent to. So there are many ways to solve this. Okay, one way to solve this is using truth table. Okay, so with truth tables it becomes exceedingly simple to do it. Okay, so let's try using truth tables. So let's write a P here, let's write a Q here. Okay, and let's write a not P here, and let's write a not Q here. Okay, and then what we do is whatever I need to compare with, not P by implication Q. Oh, okay. Let me just do P by implication Q. Okay, and let us do not P by implication Q. This is what I need to compare with. Okay, let's first see what the truth table for this looks like. The method is simply make the truth tables. The truth tables which are equal, that is in the final column, if the ones and zeros actually match, okay, same set of ones and zeros, then you have that the function will always behave similarly. Both the propositions will behave similarly, and they are logically equivalent. So let's see. Both are false. One is true, one is false. First is true, second is false, and both are true. Okay. One moment. Two. Okay. Okay, good. So negation of P. So P is 0, 0, 1, 1. Negation of P will exactly be the opposite. So instead of 0, 0, 1, 1, I'll write 1, 1, 0, 0. Okay. Negation Q. Q is 0, 1, 0, 1. I'll just write the opposite. That is the negation, right? If it is false, it's true. If it's true, it's false. False, it's true, and true, it's false. Okay. So P by implication Q. Remember the table, the answer for by implication, the truth table for by implication looks like this: 0, 1, 1, 0. We've seen earlier, right? If the combination is 0, 1 or 1, 0, then I'll output ones, else I'll output 0. So P by implication Q, the truth table looks like 0, 1, 1. Oh, sorry. I'm very sorry. The truth table looks like this, the opposite. Okay. If it so happens that one of them is if they are not equal, so 0, 1 or 1, 0, then I'll output a 0. So that is by implication. And let's do the negation of that. So 0, 1, 1, 0. Okay, we found what we need. Okay, 0, 1, 1, 0. Now let us compare the truth table for each one of them. Firstly, let me try the ones at the bottom. Okay, let me try C and let me try D. C looks like this. C is P implies Q. What is P implies Q? Uh, P implies Q, remember, looks like this: 0, 1, 1, 0, and 1. Right. If P is true, then and Q is false, then if clearly P implies Q is false. So this is what it looks like, and these two do not match. So C is not the answer. What does the truth table for D look like? Q implies P. So Q implies P. Okay. This is false when Q is true, P is false. Where is such a place? Q is true, P is false. So this corresponding place it will be false, and the other place it will be 1. Right. That is the definition. That is the truth table for implies when I mentioned it earlier. Right. So clearly these two also do not match. So C and D are not my answers. So at this point, I need to make a truth table for A and B. Okay. Let's try A and B. So what is A? A says not Q by implication P. not Q by implication P. And what does B say? B says P by implication not Q. Okay. So what does not by implication Q look like? Let us look at not Q, not P, and just simply make the truth table for the by implication. So this is not Q. Okay, this is P. Simply make the by implication table. That is when they are not equal, when it's 0 1 or 1 0, then we give a 0, else we give a 1. So it's 1 0. Okay, on top we have a 0, you have 1, then we give a 0. We have a 0, we have a 0, then we give a 1. We have a 1, we have a 1, then we give a 1. And we have a 1, we have a 0, then we give a 0. So is the truth table of A matching to what we need, not of P by implication Q? Yes. So what is our answer? A. Just for the sake of completeness, let us write the truth table for P by implication not Q also for option B. So first what you do is you locate P and not Q. Yeah. And look at their by implication. So P by implication not Q. Yeah, that truth table will also look identical. 1, because it's an either or thing. 1 1 0. So option B is also true. So option B is also true. Their truth tables are identical. So yeah, I hope it's clear so far. So yeah, the truth table method, simply make a truth table and then argue. So yeah, which of the following is true? Remember, what is a tautology? A statement which is always true. Okay. Not P and P or Q implies Q is a tautology. P and P implies Q is a contradiction. Okay. P and Q is logically equivalent to Q, and not of Px or Q is by conditional Q. So yeah, this looks a bit far-fetched, but using the truth table method, it is pretty straightforward. Okay. And I mean, if you've seen the previous method, then you can try it side by side, and if you've got the answer, then please leave it in the comments. Okay, but I'll demonstrate it again. Okay, for those of you who do not catch it the previous time. So let us do each of these. So let's try A first. Okay, not P and P or Q, then Q is a tautology. So first what I do is I write PQ 0 0 0 1 1 0 1 1. Okay, and let's write not P. That is what we use, right? Let's write not P. Okay, what does not P look like? Flip all the bits of P, 0 to 1 1 to 0, so it becomes 1 1 0 0. What do we want? This. Okay, let's do P or Q first. P or Q. So P or Q, we can simply write the truth table for all. If either of them or both of them are true, then P or Q is true. Okay, next what do? You do an AND between them. Sorry, you do an AND between them, not P and P or Q. So between these two, do AND. So what do you mean by do AND? If both of them are true, if A is true and B is true, then we get a true, right? So let's try it. Where is both of them true? Here, not here. Here. Both of them are true here. So here I have a 1, and the remaining places both of them are not true. Oh, sorry, here. Remaining places both of them are not true, so they'll give me this particular truth table. And let me call this guy A. Okay, and what we need to find is A implies Q. Okay, so A implies Q. What is A implies Q? A implies Q is false if A is true and Q is false, right? That is how the truth table was coming. So let's look at A and Q. A is true and Q is false. Is there any such case? A is true, but Q is true here. So it is not the case. So in all the rows, it is true, because there is no such case where in the column we get a false, because okay, A implies Q is false, okay, is 0 when A is 1 and Q is 0. When A is 1 and Q is 0. But such a case does not exist here, right? Does it exist? This is the only case when A is 1, and in that case Q is 1. So here all of them are 1s. Always true. Therefore, it is a tautology. I'll see if we can revisit this question later when I do some laws of algebra. But yeah, this, so we didn't even need to check the other cases actually. So, but you can check it offline, because for the interest of time I'm not checking the others. So answer is option A. Okay. Now I want to revisit some of the problems based on. I want to revisit some of the problems based on reduction, okay, using arguments. I mean, there are so many rules, modus ponens and modus tollens and so on. We can do it logically also. Let us see. Okay. If you do every problem in the book, okay, so the question is the following argument valid? Is the following argument valid? The argument is as follows. If you do every problem in the book, then you will learn discrete mathematics. Okay, that is what I tell you. Say you learned discrete mathematics. You learned it. Therefore, you did every problem in the book. Is this argument true? Is this argument good? So yeah, I would like to ask you guys, what do you think? I tell you that if you do every problem in the book, then you will learn discrete mathematics, and you learn discrete mathematics, therefore you did every problem in the book. Akanksha says may or may not be true. Okay. Okay. Others, what do you think? If you do every problem in the book, then you'll learn discrete mathematics, and you learn discrete mathematics, therefore you did every problem in the book. Okay. Yeah, Akanksha, I mean, that's right, you really can't say actually that that person did every problem in the book or not. Okay. So let's say P, okay, is you did every problem in the book. And what is Q? Q is you learn discrete mathematics. Okay, and they are saying Q. So they are saying this first. If you learn, if you do every problem in the book, then you learn discrete mathematics. And the next thing they are saying that you learn discrete mathematics. If P is true, then Q is definitely true. Okay, these are the two information that is given to us. This is one, this is two. But can we deduce that you did every problem in the book? Not necessarily, right? P implies Q means that if you did P, then you did Q definitely. Does not mean that if you did Q, you had done P. Because maybe you learned discrete mathematics some other way, right? Maybe you did not do any problem, all the problems in the book, maybe a few problems. Or maybe you learned some online tutorials. Or maybe you subscribe to a course in NPTEL, right? So there are several ways to get to Q. So this argument is not valid. I cannot say that, oh, okay, this person had actually solved every problem. That's good. But let's say I modify the problem a little, okay? If you do every problem in the book, then you will learn discrete mathematics. You have not learned discrete mathematics. Therefore, you did not do every problem in the book. Is this argument valid? That is my question. I'll give a few moments to think about it. Similar question, same flavor. Okay. Akanksha says true. Okay. Lakshmi also says true. Okay. Here a tool that we saw earlier will be useful actually. And the tool is called contraposition. So yeah. If you do every problem, okay, let us use the same assumptions. Okay. So if you do every problem as the book is P, then you will learn discrete mathematics is Q. You have not learned discrete mathematics is not Q. And therefore I'm concluding you did not do every problem in the book. Therefore not P. This becomes a bit complicated than before. You are saying P implies Q and you are saying not Q. Is it true that not P? But remember that contraposition says that this statement is logically equivalent to the following: flipping Q and P and then applying negation to both the sides. Okay. Now we are getting somewhere. So this is by contraposition. Okay. So we are saying if Q is not true, then P is not true. This is what the statement is saying. And I am saying, okay, Q is not true. We know that Q is not true. Then by 1, since Q is not true, it must be that P is not true, because that is what my question says. Therefore, P is not true holds. Thus, argument is valid. So yeah, Akanksha and Lakshmi were right about this. The argument is valid. Let me repeat myself. If P implies Q, okay, is an implication. Okay, if P implies Q, this statement that if P is implies Q is logically equivalent to its contraposition. What is contraposition? Simply flip P and Q and negate both sides. That is, not Q implies not P. Or if I want to state it in terms of the sentences, if you did not learn discrete mathematics, then you did not do every problem in the book. You can see it this way also. Because if you had done every problem in the book, then you will have learned discrete mathematics, right? So yeah, that is the contrapositive statement. And we know that not Q is true. That is, you did not learn discrete mathematics. Then uh, by the contraposition, we have that not P should also be true. So finally arguing that not P is also true, not P is true, is valid. Okay, good. So now I'll just show this. Okay, laws of logic. I think it is shown in the lecture. So you have these 8 laws that were done in the lecture. Okay, it is useful for simplifying Boolean expressions. Why is it so? Because this way you do not need to build truth tables anymore. Okay, and building truth tables for large expressions is actually a very tedious task. Okay, so simplification is a much better way to go. So commutative law means that order does not matter. I can do A or B. It is logically equivalent to B or A. Same is the case for AND. Associative law means it doesn't matter whether I do B or C or A or B in any order. It does not matter how I bracket them, provided all of them are ORs or all of them are ANDs in the expression. Distributive law is like, think of it being like A plus B times C, or more simply, A times B plus C. So A will distribute if these were integers, right? Similarly, think of multiplication and addition as and or, and it'll just simply distribute that way. Idempotent law means like if I or with itself or if I and with itself, then I get the variable itself. Okay, idempotent law. Identity law means that if I and with something that is true, then I get the same variable. If I or with something that is false, then I get with the same variable. You can verify this using truth table. Okay, I won't go in depth about this. Inverse law, okay, also called complementary law, means that if I do an or with the complement, I get true. If I do an and with the complement, I get false. Okay, and domination law. Okay, so if I do or with a variable, okay, with a true variable, okay, then the true will dominate the variable. If I do an and with false, then false will dominate over the variable. This is quite logical also. Okay, and absorption law. Yeah, this is interesting. So P or P and Q, then this P will absorb everything and become P. Or if it is P and P or Q, okay, then P will absorb everything and become P. Okay, so yeah, we can derive this using distributive law also. Okay, in fact, I think I can show it as a nice exercise. So how is this derived? Let's take this one. P or P and Q, okay, can be written as P or P and P and Q, right? P or P and P and Q, which is equal to P and Q, right? This is done by the distributive law, and this is using the idempotent law, and this is simply P and okay, there's a problem here. P or P and Q. Is there a mistake here? So P and P will be P, this will be P and Q. Okay, we'll come to it then. Yeah, probably I made a mistake, sorry. But anyway, um, we'll move on here. Yeah, come to this later. So yeah, and we missed an important one actually. De Morgan's law. This was done in the set theory week also. It simply says that if you do A or B whole complement, okay, or in other words, let me write it this way, then it is nothing but not A and not B. Okay, and if I do A and B whole complement, it is nothing but not A or not B. I change the and to or to and, I change the and to or, and then I complement both the sides, both A and B. Okay, this is very useful. Okay, this is done in the set theory course also, set theory week also. Okay, now let's so the question is, what is the complement of the expression not P and Q or R and not S? So this is pretty straightforward. If you use a particular law, then it is done. So I'll do it halfway. So complement simply means negation of which expression? This expression. Negation of the entire expression. So what law should we use here? Anyone? Okay, Kiran Kumar, P. Morgan's, Akanksha D. Morgan's. Okay. Yeah, good. Remember about this particular point. If you have to negate a large block, okay, then always use De Morgan's law. For example, here a large block is getting negated. We make smaller blocks of negation due to De Morgan's law. Okay. So what do I do? Using De Morgan's law, what do we have? Not of not P and Q, or will change to and this will get negated. Okay. Now which law do I use? Now which law do I use? Any idea? Well, we see that there are still large blocks, okay, with negation on top of them. Okay, this one and this one. So I can use the De Morgan's law again. So what I'll do is I'll change the and to or. Okay, yeah, good, Adam. That's right. I'll change the and to or. Okay. I'll change the and to or. I'll change the Q to not Q. I'll change the not P to not of not P. Okay. And again, use De Morgan's law here. And will change to or, R will change to not R, and not S will change to not of not S. So here we'll use this double negation that was talked about in the lectures. Double negation simply means not of not P is P itself. So this is P. Okay, here using De Morgan's again. Okay, this is nothing but P or not Q and not R, or this is simply S by double negation. Okay, now let us compare P or not Q and not R or S. P or not Q and not R or S. So the answer is option B. Okay, good. So let us look at another one. Okay, the expression. Okay, this is an interesting one. I'll let you guys try it for a while. The expression P or P and Q, or P and Q and R, or P and Q and R and S, and so on. Let's say this is infinitely going. Okay, let's say this expression P or P and Q, or P and Q and R. Okay, it's not, and it's or P and Q and R and S, and it's going P and Q and R and S and T and so on, and it'll go till infinity. Can you tell me what it is logically equivalent to? The options are saying false, true, P, P and Q. Okay, Akansha is saying P. Okay, so the others also try. Try to use one of the laws here. Can this be done by this? Yeah, I think this can be done. Okay. Others, Akanksha is saying P. Adam Ahmad is saying I would just solve it taking the values in. Taking the values in. I did not understand, Adam. Mm, taking the values in. So you mean you would try like 1 first and 0, something like that? Adam. If you mean that, okay, if you mean that case based, like I'll take 1 first and I'll take the value as 0, yeah, then that will also work. If you mean that. Do you mean? Okay. I mean, there are various ways to approach this problem. Okay, so let me look at the most straightforward way using laws. Okay, um, so what I can do is I see that P is common among all of them. Okay, looking at what the pattern is, if it is common, then I can use the distributive law. Okay, distributive law simply talks about taking common. Let's do it as Boolean expression. Let's do it as Boolean expression. Let's do it as Boolean expression, Adam. Okay. You mean like what I'm doing using the laws? It is not Boolean expression, but it simplifies. It's not Boolean expression, but it simplifies. Right. Okay. I'll do using the laws, Adam. Tell me if this is what you thought. Okay. So yeah. So here you see that p is common here, so I can take it common, like I showed you, like you take it common between integers, right? So here let me take it common, p, or okay, I take p common, okay, and then okay, Kiran is saying c, I take p common, and here I do q, or q and r. Okay, here there is an and, p and q, and I took p common from here, and from here also I take p common, so I'm left with q and r and s, and so on. So at this point, use absorption law. I know because of the absorption law that p, or p and q is equal to p. I'll simply, absorption law means I'll simply absorb this p, absorb this entire expression actually into p. So it is in the form of absorption law because there is p followed by some other proposition. So this is equal to p using the absorption law. So yeah, Akanksha, Kiran, yeah, you are correct. The answer is p. You may not have done it this way. Okay, another way to do it, okay, could be this. P, take p common from the entire thing. So if I take p common from the first variable, what do I get? I get a 1. Then what do I do? An or, again the same thing, q, or q and r, or q and r and s, or and so on. This is what I get. Great. And now we use the we use one of the laws above, okay, that says that if I take 1 with anything, okay, and if I take, oh, I want to tell you the exact, yeah, if I take domination law, if I take a truth value, okay, or anything, I'll always get true. If I get true or anything, I'll always get true, which is equal to p, sorry, there will be p and true, because this entire thing will be 1 by domination law, and by identity law this is equal to p, because p and anything true is equal to p. This is another way to do it. Adam says pretty much the same thing. I love this expression. Taking or as plus and as, oh, okay. Yeah. Actually, that is a helpful thing. Yeah, right. Adam, yeah, it's a nice way to represent it actually. You know, a lot of, but I'm sticking to the notation from the NPTEL lectures. That's why I'm not writing or as plus and as. So what Adam is saying, we can take or as plus and as multiply or dot, and simply write this expression as p plus pq plus pqr plus pqrs, and then you know things like distributive law and so on become very intuitive. So yeah, but what I thought you were saying, Adam, was before, what I thought you were saying was that, you know, you do when p equals 0, okay, and then you do when p equals 1, and then show that, you know, this will always be 0 and this will always be 1. This is a third way to do it, by the way. You can try this when p is 0, when p is 1. Okay, yeah, that's one way to write this expression as, and it will be simpler that way. But I'm sticking to the notation that was given in the NPTEL lectures. Okay. Okay. Okay then, good. um so yeah, what is the time? We have this question. Okay, yeah. So yeah, let's solve this question. Okay, again, the question is as follows. I am given a boolean expression. I want to simplify it. Okay, I'm given a boolean expression. I want to simplify it and then check whether it is one of them. Okay, the given expression is as follows: p or not q or r, and p or not q or not r, and p or q or r. So this is given to us. We want to check whether it is equivalent to one of these. So the idea is to simplify this expression using the laws that are given to us. Okay. So what can we use? So I cannot use De Morgan's law because there is no large complement. Okay. I cannot use most of the laws, but if something is common, always remember we can use the distributive law. We see here that this expression is common and this expression is common, right, between these two. Therefore, we can use the distributive law. What does the distributive law say? A, okay, or B and A or C equals to, take A common, or B and C. This is the distributive law. Okay. Similarly, I'm taking this as A and this as B, this as A and this as C. Okay. This has my A, B, A, C. C. So we take A common, P or not Q, okay, and do an OR, okay, and put a bracket, B and C, that is R and not R, and remaining expression. Okay, so far I think everyone is getting it. So yeah, please stop me if there is any hiccups. Next, this becomes P or not R, or R and not R. So we know from the inverse law that R and not R, any statement and its complement is always equal to 0, is always equal to false. Okay, this is false. This was by distributive law. Okay, distributive law is nothing but this. This is by inverse law. Okay, and P and sorry, P or Q or R. Okay, so we keep these brackets, otherwise we'll get confused. So anything or false will be the variable itself. So by inverse law, okay, sorry, not the inverse law, by identity law, that's right. By the identity law, we know that this will compute, yeah, this will bring the identical variable. If identity law states that if A or false will be equal to A. So finally this is what we get. And now what we can do is you can take, okay, so now what we can do is we can take P common, we can take P common from here, again using the distributive law. Okay, if I take P common, it becomes P or not Q, okay, and Q or R. Is it not? So now again, this is in the format of distributive law. So Q will distribute here. So to simplify, it becomes P or not Q and Q, or not Q or R. But we know that not Q and Q is nothing but false. So this is P or false or not Q or R. And anything or false, okay? Now again, we use the identity law. P or, so anything with false or with false will give you the same by identity law. So what is your answer? P or not Q? P or not Q or R? P or, okay, it should have been P and somewhere I made a mistake. Oh, okay. I think I made a mistake in typing the question then. I'll verify it later, but I think this should be P and not Q or R. I'll verify it once. But if you are doing it side by side, please verify it, okay? I'll try it again offline. If it so happens that there's a mistake in the question, I'll correct it and post the notes. Yeah, but for the timing, I do not see an error here. Because on taking common, I get an or here. Yeah. Okay. Okay. Here's the error here. So this should have been and. This should have been and, yeah. Sorry. So this will be an and, because the distribution will cause an and here, and here is the and. So P or not Q and R, yeah. Sorry, the question was correct. I was wrong. So the solution is B. Yeah. Oh, there's a message. I got P, not Q or R. Okay, let's see. Adam says you got P and, I think you mean and here, not Q or R. So are the steps that I did matching, Adam? You got P and not Q or R. Okay. Are the steps matching, Adam? I think you should look in this part, because this is where the first we encountered P or something. But yeah, I could be wrong too. But right now I do not see. Okay, Adam, will take it offline. But can you look from third step? Okay, so let me see. So you mean first, second, third? Is this the one third step? Yeah, okay. This is the third step, right? So what happens in the third step? We take P common. So we take P common and we do P or q complement and q, or yeah, that's what we do, no? So if we have a or b and a or, sorry, not a, yeah, a or c, then what do? We take a common, okay, or b and c, right? So um so what is a here? This is a, this is b, this is a, and this is b. So a or b and c, a, which is p, or b and c. Yeah, b is q complement and the remaining. So step 3. Oh, okay, I was taking p and p or q, not q. Ah, okay. P or q or r, not q. Oh, okay. Or not q. Okay. Okay. Yeah, good. Okay, so I think the doubt is clarified, Adam. So yeah, we are. Oh, okay, good. So we are almost wrapping up now. Okay, this is the final question. So yeah, I would like you guys to participate in this. Okay, the question is as follows: consider the following statements. Okay, if I am sick, there will be no lecture today. Either there is a lecture today, or the students are happy. The students are not happy. This is what I know. What can be inferred from the above? Is it that I am sick? Is it that I am not sick? The students are sick. The students are happy. Please look into this one. Look at the statements. Stare at it. I'll give you like a few minutes maybe. If I am sick, there will be no lecture today. And either there is a lecture today or the students are happy. The students are, oh, okay, that was quite fast, Akanksha. Okay, Akanksha says B, I am not sick. Okay. Okay. So the remaining people also please try. What I would recommend is assign, like I did before, please assign propositions. Looks B for me too. Okay. Okay, good. So what I would say is um, assign propositions. Okay. Say S is I am sick, and L is there is lecture today, and let's say H is students are happy. Okay. And what I would say is rewrite each of these statements. Rewrite each of these statements using, S, L, and H in terms of S, L, and H, and try. Maybe I'll give you another minute. So I mean, um, we can immediately see that question option D is not an answer, because clearly we are saying that the students are not happy, and here we are saying that the students are happy. How can that be? Right. So question B is clearly not the answer. And logically, if you use your common sense, then um, we are not talking about sickness of any student, right? It's only about I am sick, or the students are happy, or is there a lecture today, and so on. I cannot suddenly derive that the students are sick. So option C is also you know out of possibility. So there are only two options left. Which one of the two is my answer? Okay, let's see. Um. Okay, what did you guys answer? Okay, Akanksha and Adam would say B. Yeah, Akanksha, Adam, yeah, good. Both of you are correct. Um. So yeah, let me number them: 1, 2, and 3. So one says, if I am sick, there will be no lecture today, which means negation of L. Okay. And a second statement is, either there is no lecture today or students are happy. Either there is no lecture today, L, not L, or students are happy. Or students are happy. Oh, sorry. H is students are happy. Next. The students are not happy. Okay, good. Now let's see. Let's look at 2 and 3. Okay. Not L or H. Either there is a lecture, either there is no lecture today, or students are not happy. Right. And we know that students are not happy. So if not H means students are not happy, then not L or H is yeah, this is true only when not L, right, by property of or. So either there is no lecture today, or students are happy. So and we know that students are not happy. So clearly this cannot be true, right? We cannot have students happy and not happy at the same time. So it must be that not L is true, because we said that this statement is true. Or yeah, is true. Yeah, that's right. Is true. We said that this statement is true, and this statement can be true only when not L, because we already know H is false. That is, happy is false, right? So now what do you have? So we have this new information. Let me call it 4. Oh, okay, wait. Is it there's no lecture today, or the students are happy? Students are, yeah, that's right. Okay. Now what do you have? What can I also write this as? I can write this as its contraposition, right? So if L is so I can write it as contraposition. The contrapositive is L implies not S. Oh, okay, sorry, I made a mistake. L or H is true only when there is a lecture. Sorry. because clearly not h is false. Sorry, I made a mistake. um, the student are not happy, okay, means that there was a lecture today. And by the contraposition, by contraposition of 1, by contraposition of 1, we have that not s is true, because L is true. That is, there was a lecture today. Okay. And if there was a lecture today, then I'm not sick, which means that I'm not sick. So I am not sick. Answer is okay. Good. So with that, we've come to the end of the session. And I will be uploading this session, the recording of the session, to YouTube like always. And I will also be uploading these notes to the drive. I hope you guys have access to the file. So next time again, we'll meet on Tuesday at 6 p.m. Okay, same time. And next time the topic is relations, I believe. So yeah, I hope you meet that time. For now, we've come to the end of the class. Okay, and have your dinner. And okay, yeah, thank you, Adam. Have your dinner and good night and happy Independence Day once again. Okay. Yeah. Yeah, Adam. Happy Independence Day. Thank you.